Hello students, let me begin with a simple thought. Have you ever seen an airplane flying across the sky? From where we stand on the ground, the airplane looks no bigger than a tiny dot, even though it is actually more than 70 meters long. In physics, we often do something very similar. Instead of worrying about the detailed size and shape of an object, we sometimes treat the entire object as if all its mass is concentrated at a single point. This idea is what we call a point mass. By doing so, we can study motion in a simpler, more elegant way without missing the bigger picture. So what exactly is a point mass? The definition is straightforward. An object is said to be a point mass when the change in its position is very large compared to its own size. Mathematically, if displacement delta x is much greater than the size of the object, then we can treat the object as a point mass. Think of an airplane flying from Delhi to Mumbai. The distance traveled is more than 1,000 kilometers, while the airplane itself is only a few dozen meters in length. Clearly, its size is negligible compared to its journey, and so we can treat it as a point. Let's see some classic illustrations. Imagine a person standing on a railway platform. For the train passing by, that person can be considered as a point object, since the person's height and width are negligible compared to the length of the train. Another example, Earth revolving around the Sun. The Earth's diameter is about 12,700 kilometers, but the distance between the Earth and the Sun is nearly 150 million kilometers. The Earth's size is tiny in comparison, so it is modeled as a point mass. Or take a cricket ball flying across the field. Its diameter is about 7 centimeters, while its path covers more than 100 meters. Once again, we treat it as a point mass to simplify our analysis.
Of course, the point mass idea does not always work. There are situations where the size of the object is comparable to the distance it moves. In such cases, ignoring the size leads to wrong results. For example, think about a ceiling fan blade rotating. Every tip of the blade moves in a different circle, and you cannot replace the entire blade with a single point. Or imagine a tumbling box rolling down a slope. Different corners of the box follow different paths. Here, size and rotation matter, and the point mass approximation fails. So remember, the decision to treat an object as a point mass depends on the scale of motion we are studying. Let's solve a quick numerical to cement this idea. The Earth's diameter is about 1.27 times 10 to the power 4 kilometers. Its orbital radius around the Sun is about 1.5 times 10 to the power 8 kilometers. Can we treat Earth as a point mass while studying its orbit? Step 1. Calculate the ratio. Ratio equals diameter of Earth divided by distance to Sun. That is 1.27 into 10 to the power 4 divided by 1.5 into 10 to the power 8. Step 2. Simplify. This gives approximately 8.5 into 10 to the power minus 5. Since this ratio is extremely small, the Earth's size is negligible compared to its orbital distance. Therefore, yes, Earth can be treated as a point mass in orbital motion. This simple calculation shows the power of approximation in physics. So let's quickly recap. A point mass is an object whose dimensions are negligible compared to the distance it travels. It is a powerful simplification tool, allowing us to study motion in an elegant and manageable way. A passenger relative to a train, a cricket ball in projectile motion, or even the Earth revolving around the Sun, all are examples where the point mass model works beautifully. But when object size is comparable to displacement, or when rotation and internal structure matter, this approximation fails. I hope this session gave you a clear idea of when and why we use the concept of a point mass in physics. See you in the next session, where we will unfold yet another fascinating building block of motion.